Hello, students. So, continuing our lectures on magnetic relaxation and resonance, we'll discuss nuclear magnetic resonance. Now, it's nuclear magnetic resonance. Now, atomic nuclei has an angular momentum and associated with it the magnetic spin. Atomic nuclei has an angular momentum and a magnetic spin associated with it. So, when someone talks about nuclear spin, that is I, nuclear spin I, one what one refers is the largest observable value of the component of angular momentum. So, this is actually this component of angular momentum in units of h cross along a specified direction. Along a specified direction, and this direction is of an applied magnetic field H, and it's preferably along the Z direction. So what we see is that if we are applying a magnetic field HZ, due to which the angular momentum of the atomic nuclei, it has a component along that direction in the units of H cross, and that is the nuclear spin. So, if Hz is a total magnetic field applied, then the total angular momentum. So, the total angular momentum is given as point 5 plus 1 H cross root 1 by 2. Now, when we say about components along the Z direction, what we mean is the values of the magnetic quantum numbers Mi. So if we have I, we will have the component Mi, and Mi will take values from minus I to I. So if this is the total angular momentum, and we know that there is there is relationship between angular momentum and magnetic moment. So the magnetic moment again will be equal to uh, E by 2 mpc into G into ma. So this is actually the proton mass, and G is, or one should say, one by G. This is the gyromagnetic ratio, because the ratio between the magnetic moment and the angular momentum is called the gyromagnetic ratio. So here mu, or m by mu is equal to 1 by G. So that is how this G is the gyromagnetic ratio. So if this is the value of mu, so the maximum component will be the mu applied in the z direction, mu in the magnetic moment in the z direction. Its maximum component will be equal to, right, E by 2 mpc. Change that. There will be G, and only thing will be M will be replaced by H cross I. And so we have H cross by 2 mpc into G into I, and this quantity, had it been M, had it been mass of electron, would have been mu b. So we know that EH cross by 2 MEC this is known as the gyromagnetic, the Bohr magneton. Similar to that, this is mu n. We call it as mu n, and it's called nuclear magneton. Mu n is the nuclear magneton, and its value is 5.049 into 10 to the power minus 24 erg per Gauss. Now, as in the case of atoms and nuclear also, in nucleus also, if there is an external magnetic field H applied, the magnetic moment mu associated with the nucleus will precess along this H. Is the H applied. Magnetic moment will also precess around H mu with a frequency called the Larmor frequency. And that frequency is omega L, and it is equal to minus G E by 2 M P C into H. Okay, now when we are applying a magnetic field, it also produces splitting as we get in. It's actually the nuclear Zeeman effect. So it is also applicable in the case of nucleus. So this is the splitting of the energy levels. For example, if we consider the example Na23, which is an isotope of sodium, so it has angular momentum, nuclear spin as 3 by 2. So the possible components of mu along the field directions in units of g mu n. So as we know that mu max is equal to g mu n into I. So the components will be 3 by 2, then 1 by 2, minus 1 by 2, and minus 3 by 2. That is from I2 minus I. So the energy level will again will split according to that. So can show the splitting here. So we'll have 3 by 2 level here, then 1 by 2, then minus 1 by 2, and then again minus 3 by 2, and this is for I is equal to 3 by 2, and so we will have transitions taking place, and the difference between each level is will be G mu n into H. So the transitions are possible only between the successive levels. So they cannot transit between this and this level. So we can say that delta I should be equal to 1. Plus minus 1, you can call it plus minus 1. So successive levels will have that condition. And the energy will be G mu n into H. Now, the condition required for resonance absorption it's not delta I, it's delta mi, the selection rule. So since so this also implies one thing. So delta mi is equal to plus minus 1. So it also implies that the resonance may be observed in an alternate magnetic field. So if we have an alternating magnetic field of frequency, say omega, then we can see that H cross omega is equal to G un into H, and then we put the value of mu n as uh, H cross by 2 mpc into H. So this frequency is again equal to the large mode frequency mu L. If you apply a magnetic field of say 10 to the power 24 Gauss, then the nuclear resonance frequency will be omega L by 2 pi. 2 pi is done to convert angular frequency into normal frequency, and this lies in the radio frequency range.